Okay, so we'll start now. In the last lecture of analog and digital electronics, we have started with the basics of differential amplifier, right? We have seen what do you mean by differential amplifier. So whenever we have the two different inputs, right? And the difference of these two input signals will get amplified whenever we talk about the differential amplifier, and that is why it is also known as difference amplifier. So in this particular case, what we have seen is we are available with two inputs and one output. Say my input will be V1 minus V1 and V2, and output would be V0, right? So that V0 is nothing but the difference between the two inputs, that is V1 minus V2, and it gets multiplied by its gain, which is known as differential gain. So we have introduced you to the differential gain, which is denoted by AD, right? So this AD is nothing but the constant of proportionality, right? With which the differential amplifier will amplify the difference between the two input signal, and this is the reason why it is called differential gain, right? So ultimately we can say that we are available with output V0 is equal to AD times VD, where VD is my differential input, which is V1 minus V2, right? Then we have seen this output equation is equal to ADVD. It is not ADVD only. It also depends on one parameter which is known as common mode voltage. Okay, so there will always be a common mode voltage VC which is available at these two inputs, and it is nothing but the average of two input signals V1 plus V2 by 2. So because of this common mode voltage, we will be available with one more gain which is known as common mode gain AC. Right. So now you can see the output equation does not depends only on this V0 equal to AD plus VD, plus also it depends on common mode gain and common mode voltage. Okay, so this is what we have seen, the output voltage equation of differential amplifier, right? So we have seen this common mode gain, but as we know, this common mode voltage is not the desirable one. Okay, so we must eliminate this voltage, we must reduce the effect of this common mode voltage, and that is why we have one parameter which is common mode rejection ratio. Okay, so when the same voltage is applied to both the inputs, what will happen? The difference amplifier is said to be operated in a common mode configuration, right? So many disturbance signals, noise signals will appear as a common input signal to both the input terminals of the differential amplifier. Okay, and such a signal, a common signal, should be rejected by the differential amplifier. Okay, so the ability of a differential amplifier to reject a common mode signal is expressed by this ratio known as common mode rejection ratio, denoted by CMRR. Okay, it is symbolically represented by rho, and it is nothing but the ratio of differential gain to the common mode gain, right? So ideally, the common mode voltage gain is equal to 0. So the ideal value of CMRR is equal to infinite. Okay, so this is our ideal value, and we know very well, larger is the CMRR, better is the operation of the differential amplifier, right? And also we have defined the expression of output voltage in terms of CMRR also, and that equation was AD times VD into 1 plus 1 over CMRR into VC by VD. Okay, so if you look at this equation, it explains that CMRR is practically very large, though both this VC and VD components are present. Okay, so the output is mostly proportional to the different signal AD VD only. Okay, the common mode signal, the common mode component is greatly rejected. As we know, the common value of CMRR is very much high. So this component will become almost zero, right? Such that the entire output voltage will depend on this only, AD times VD. Okay, and then we have seen some features of this differential amplifiers, right? And we have also solved one example based on this differential amplifier. Now today, what we are going to see is we are going to understand the operation of this differential amplifier in terms of some circuit diagram. Okay, and as I have discussed earlier, that whenever we talk about the operational amplifier circuits, they are made up of some transistor. Okay, it may be MOSFET, it may be BJT, it may be any other transistor from transistor family, but we do have this transistorized differential amplifier circuit, right? So what we will do, as we know that differential amplifier are having two number of input signals. So in this particular case, what we are going to do is I'm going to use emitter bias circuit, two identical emitter biased circuit. Okay, so let us start with this. Say I have one supply voltage. This is my first transistor. And I am providing supply over here, right? This is base. So this is base B1, collector C1, and emitter E1 of first transistor. Okay. Now we are providing the supply plus VCC to the collector terminal and minus VEE to the emitter terminal. The resistance which is connected to emitter terminal, let us call it RE1, and the resistance which is connected to collector terminal, let us call it RC1. Okay, so this is one complete emitter biased. Okay, now what I have told you that we are going to use two emitter bias circuit. So this is my second circuit which I have taken, right? Now this time this resistance would be RC2, this is collector terminal, this is base terminal, this is emitter terminal, and this is resistance. Okay, so these are my emitter biased circuit. And as I have told you, these are identical circuit. Now what do you mean by identical circuit? See, if I talk about transistor Q1 and transistor Q2, right, then this Q1 and Q2 both are identical, right? What does it mean? They will produce same characteristics, same VI characteristics if we apply certain amount of voltage across these two transistors. Okay, so the same magnitude of the characteristics of this both the transistors will be same, right? Then if we talk about the collector resistances, then value of this collector resistances RC1 and RC2 are also same. Similarly, value of emitter resistances RE1 and RE2 are also the same. And talking about the magnitude of supply voltage, magnitude of plus VCC and minus VEE are also same. Okay, so we are available with two identical emitter biased circuit, right? Now the differential amplifier can be obtained by using such two emitter bias circuit. Okay, and this is achieved by connecting emitter E1 of Q1 to the ammeter E2 of Q2. Okay, now let us see this circuit. Okay, I am taking the circuit. Right, this is my two different ammeter circuits. Now what is the change? That the ammeter of this transistor Q1 and ammeter of this transistor Q2, these two are to be connected together, right? So what I am doing, I am removing these resistances and connecting the two terminals together. Now what will happen to these two resistances? Two resistances will appear in parallel to each other, and which will make one resistance. Let us call this resistance as Re. Okay, and magnitude of minus VEE is already same. So this Re is nothing but Re1 parallel to the Re2. Okay, so now this ammeter connections are there. Now what I am doing, see, for the simplicity, I am changing the position of this transistor 2. Okay, so I am taking it outside. This is my emitter terminal, like this. Okay, so this is base terminal 2. Now talking about the collector terminal, right? So base of talking about the base terminal, so base B1 of Q1 will be connected to input 1. Okay, let us say this input be Vs1, right? So base of collector 1 will be connected to input 1, and that is Vs1. Okay, this is internal resistance of the supply voltage Vs2. Similarly, the base 2 will be connected to second input, that is Vs2, and it is grounded. So this is my base 2, and this is internal resistance Rs2 of supply voltage 2. Okay, so now these two are my source signals. You can see Vs1 and Vs2. Right, now coming back to the collector terminal, right? So the supply voltages are measured with respect to ground. Okay, so you can see we will take the output between this collector C1 of Q1 and collector C2 of transistor 2. And talking about this, definitely these two supply voltage will get together, right? So VCC will now made common like this. Okay, and as we know, value of RC1 and RC2 are same, so we'll call it RC only, right? Now what we need to do is we need to consider the output. Okay, so here is what we are going to take output. Okay, we are going to measure the output voltage over here. So this is my differential amplifier. Okay, and this differential amplifier configuration is known as dual input balanced output differential amplifier. Right, now why it is called this balanced output differential amplifier. Let us try to understand this particular case. Now here you can see this particular amplifier can also be known as ammeter coupled differential amplifier, right? So here you can see the output can be taken between two collectors. Please mute yourself. So the output can be taken between two collectors or in between one of the two collectors and the ground. Okay. So when we take the output between the two collectors, okay, none of these two terminals is grounded, then it is called balanced output, or you can also call it double-ended output or floating output. Okay. So whenever we have this scenario where we are going to measure output voltage like this, it is called balanced output or double-ended output or floating output. Right. Now another way is we are going to measure the output between any of the collector and the ground. Okay, so now in that case what is going to happen? See, if I talk about this particular part, okay, then here is my collector C1 and another end is grounded. Okay, and I'm going to measure output voltage over here. Okay. So this particular output will be called as unbalanced output, or it is also known as single-ended output. Okay. And this one is the complete circuit diagram of such a basic dual input balanced output differential amplifier. Okay. As we can see, the output is taken between two output terminals, none of them is grounded. This is the reason why it is called balanced output differential amplifier. Okay, so this is what we are available with now, one complete circuit diagram of a differential amplifier. Okay, now the question is how this circuit will behave when we will provide the two input signals V1 and V2 to this particular circuit diagram. Okay, how our input will get amplified, right? So let us try to understand the operation and analysis of this differential amplifier. Okay, and whenever we talk about the operating principle of this particular circuit, then this circuit may be operated in two different modes. One is known as differential mode operation, and second is known as common mode operation. Okay, so let us start with the first kind of operation, which is known as differential mode operation of differential amplifier, right? So in the differential mode, the two input signals will be different from each other. Okay, so we will consider the two input signals which are same in magnitude but 180-degree out of phase. Okay, so these signals with opposite phase can be obtained from, say, center tap transformer, we can say. Okay, so let us start with the circuit which is used in differential mode operation. Okay, the circuit will be same. Again, we will be using two ammeter biased circuits, right? So we will have one VCC voltage, which is our supply voltage, plus VCC. Then two equal values of collector resistances will be there, right? This is my collector terminal of the transistor. This is emitter terminal of the transistor. Again, this is collector terminal, emitter terminal, and we know these two emitter terminals are connected to each other, and they are connected via some resistances RE. Okay, this is collector resistance RC. Right. Now, the supply voltage needs to be given to the base of transistor Q1 and to the base of transistor Q2. Okay, both are having its own source resistances RS1 and RS2. Now, as I have told you, what I am doing, see, the input available at this RS1 is this one, sinusoidal, and the input providing at terminal 2 is 180 degree out of phase, that is like this. Okay, and how we will achieve this two opposite phases? By using a center tapped transformer, right? So here is what we are going to have, a center tapped transformer. Right, this is my center tap transformer where I am providing a sinusoidal source to the primary of the transformer, and secondary of the transformer is tapped at the midpoint of the secondary winding like this. Okay, let me shorten this. Okay, this is RE. Okay, so one end of the secondary is connected to input 1 and another end of the secondary is connected to input 2. Okay, now whatever supply voltage will be available, that will be 180 degree out of phase to these two transistors, transistor Q1 and transistor Q2. Okay, so let us say this is my Q1, this one is Q2, and here we are providing negative VEE voltage. Okay, so this is our circuit diagram for differential mode operation. Remember, what do you mean by differential mode operation? The two inputs are same in magnitude, but they are out of phase by 180 degree, right? And now we are going to measure some output voltage over here, okay, between these two collector terminals. Okay, and as you can see, none of the collector terminal is grounded. That means we are available with balanced output, or you can say double-ended output, or it is also known as floating output, right? So now what happens in this scenario, in this particular circuit, and what kind of output voltage we are getting over here? Okay, see, in this case the first positive cycle is there, and in second case, second half cycle is my positive cycle. Okay, so what will be the output over here? Whether first cycle will be positive or second cycle will be positive. Okay, let us try to understand this operation, right? So we have assume here that the sine wave on the base of Q1 is positive going. Okay, that is what I have drawn over here, and it is negative going on the base of Q2, right? So with a positive going signal on the base of Q1, an amplified negative going signal will develop on the collector of Q1. Okay, so at this particular angle over here, the output voltage will be like this. Okay, we know how transistor works. Okay, so we will get this negative going output voltage which is available at the terminal C1 of transistor 1, and here is what positive due to this positive going signal, current through IE will also be increased, and hence a positive going wave will develop across the resistance RE. Okay, and due to negative going signal on the base of Q2 over here, what will happen? An amplified positive going signal will develop on the collector of Q2. Okay, so now if we talk about the voltage over here, it will be like this. Okay, a positive going voltage will be there, right? And a negative going signal will develop across RE because of the emitter follower action of Q2. Okay, so now if we talk about this resistance RE, because of Q1 a positive going signal is developed, because of Q2 a negative going signal is developed. Okay, so signal voltage across this emitter resistance RE due to the effect of Q1 and Q2 are equal in magnitude and 180-degree out of phase due to the identical pairs of the transistors. Hence, these two signals will cancel each other, right? What they will do? They will cancel each other, right? And there will be no signal across the emitter resistance. Okay, so there is no AC signal current flowing through the emitter resistance, and hence this RE in this case does not introduce any kind of feedback. Okay, basically this emitter resistance will introduce negative feedback, but in our case this RE does not introduce the negative feedback. Now coming back to the output voltage V0, right? So V0 is nothing but the output taken across the collector of Q1 and collector of Q2. Okay, so the two outputs on collector 1 and 2 are equal in magnitude, you can see, but they are opposite in polarity. So the output V0 is nothing but the difference between these two signals. Okay, so suppose my output over here is say 10 volt. Okay, and output over here is again 10 volt, but they are opposite in polarity, so this will be minus 10 volt. So output will be plus 10 minus minus 10, and it will become plus 20. Okay, so the difference output V0 is twice as large as the signal voltage from either collector to ground. Okay, so we will have output voltage which is twice the input voltage, like this. Okay, so this is how the differential mode operation will take place in case of differential amplifier, right? And another kind of operation we know is common mode operation. Okay, so what we will do in this common mode operation, the signal applied to the base of transistor Q1 and Q2 will be derived from the same source. Okay, so now we will use a single source to get the output voltage. Okay, let us try to understand this phenomena also. Okay, so we will be using the same circuit over here. Now what is not there is this amplifier, transistor, transformer, sorry, not transistor, transformer. Okay, so this is the circuit diagram which we are going to use for common mode operation of differential amplifier. So let us forget about all these inputs. We are going to consider one more input. So as we have discussed that in this mode, the signal which are applied to the base B1 and B2 of transistor Q1 and Q2 are equal in magnitude as well as in phase. Okay, so they are not 180-degree out of phase. So what we are doing now, we are using the same source over here. Okay, say Vs1 will be equal to Vs2. The same voltage is applied to the second terminal also. Okay, so this is my circuit, right? So now if I talk about the input over here, then we will have a positive going input Similarly, over here also we will have a positive going input, right? Now understand key operation. Okay, so you can see in phase signal voltages at the basis of this transistor Q1 and Q2 causes in phase signal voltages to appear across this emitter resistance Re. Okay, now they will add together. Okay, so this Re carries a signal current and it will provide a negative feedback now. Okay, and this feedback will reduce the common mode gain of differential amplifier. Okay, so the two signals cause in phase signal voltage of equal magnitude to appear across the two collectors of Q1 and Q2. Now the output voltage is nothing but the difference between the two collector voltages which are equal and also in phase. Okay, so suppose 10 volt appears at each ender, then output will be 10 minus 10, which is equal to 0. Thus the difference output V0 is almost 0, or you can say negligibly small. Okay, ideally it should be equal to 0. Okay, so here at C1 what we are getting is definitely negative going signal will be there, and at C2 we will get same negatively going signal, because this is what we are available at the base of Q1 and Q2. So my output voltage will be equal to 0 in common mode operation, and this is what we require. Okay, so we are greatly reducing or eliminating the effect of this common mode voltage. Okay, so this is how the differential amplifier is going to work. Okay, so now we know very well this circuit for differential amplifier. Okay, so there are different configurations of this differential amplifier circuits. Mainly we are using total 4 number of configurations based on how we are going to take this output voltage. Okay, so the first configuration is already seen by us, and this is known as dual input balanced output differential amplifier. Dual input balanced output differential amplifier. Then second one is dual input unbalanced output differential amplifier. Unbalanced output differential amplifier. Then third configuration is we will provide a single input. So we will have single input balanced output differential amplifier, and then the last configuration may be single input unbalanced output differential amplifier. So this differential amplifier uses two transistors in common emitter configuration. Okay, so if we take output between the two collectors, it is called balanced output or double-ended output. If the output is taken between one collector with respect to ground, it is called unbalanced output or single-ended output. And if the signal is given to both the input terminal, it is called dual input, while if the signal is given to only one input terminal and other terminal is grounded, it is called single input or single-ended input. Okay, so out of these 4 configurations, the dual input balanced output is the basic differential amplifier configuration, and this is what we have seen in this particular circuits. Okay, this is my dual input balanced output differential amplifier configuration. Okay. Now if we ground one of the input terminals, then it is called single input balanced output amplifier. And if you are going to measure output voltage between one of the collector terminal and the ground, then it is called unbalanced output. Okay. So the operation of this dual input balanced output differential amplifier in differential mode and common mode we just discussed, right? So this configuration is also known as symmetrical differential amplifier, right? So now we know that we are available with total 4 configurations of this differential amplifier, and we know that this differential amplifier can be operated in 2 ways. One is differential mode and second one is common mode, right? So now let us try to understand or try to analyze this differential amplifier. Okay, so we will do the analysis of differential amplifier in 2 phases. One is called DC analysis of amplifier and another one is called AC analysis of the amplifier. Okay, so let us start with the DC analysis of differential amplifier. The first part is DC analysis of differential amplifier. Okay. Now the question should arise in your mind, what do you mean by this DC analysis? Okay. And we know very well in basic electronics subjects, I have told you why we are using the DC analysis of any switch, any semiconductor device, to obtain the operating point values, right? Q point, we were talking about the Q point. So if transistors are used, then what are the operating points? The operating points are ICQ and VCEQ. Okay, so in case of transistor, the operating points are ICQ and VCEQ. Okay, so we are drawing one DC load line and the characteristics. Okay, so we are getting the maximum point on the horizontal axis and maximum point on the vertical axis. Okay, and then we will draw a straight line covering both the points, and then we will have the actual characteristics of the device. So whenever this DC load line intersect the operating characteristics, that will give us the operating point of the device. Okay, let us try to understand with the help of some graphics. Okay, see, I will get these 2 maximum points over here. Okay, then we will have one characteristics. Let us say this is my characteristics of one particular device. Okay, so this point, intersecting point, will give us these 2 values like this. Okay, so this is our VCEQ value and this is my IQ value. These are called as operating points of the transistor. Okay, and this is why the DC analysis is required. Okay, so here the supply voltages will be DC while the input signals are AC. Okay, so DC equivalent circuit can be obtained by simply reducing the AC input signals to 0. Okay, we are going to analyze this, see the DC analysis of differential amplifier, and as we know, if we talk about this particular circuit, then here you can see the supply voltages are DC. Okay, so there is no problem with this DC supply, but as you can see, the input signal which is to be amplified is alternating in nature, right? So in order to get the DC equivalent circuit of this differential amplifier, what we need to do is reduce these AC input signals to 0. Okay, and by reducing this AC input signal to 0, we will be getting DC equivalent circuit. Okay, so let us try to draw the DC equivalent circuit of the differential amplifier now. So we do have the collector resistances which are same in value. Okay, so this is my positive VCC supply. This is collector resistance is RC. Now we will have these transistors. Okay. Both these transistors are emitter of these transistors are connected to a common point, and it is supplied by negative VEE voltage. Okay. So this is the emitter resistance RE. Now to the base of both the transistors, what we are doing, we are connecting the input signal which is AC in nature. Okay. So we will try to reduce this AC component. So what we will do, we will have these both terminals connected to ground. Okay, this is also connected to ground. Okay, so now values of Vs1 and Vs2 will become 0. Okay, and the values of Rs1 and Rs2 will now be same. Let us call this as Rs only. Okay. So this is my complete DC equivalent circuit. Okay, so this is base B1, T1 and E1 of transistor Q1. This is collector C2, base B2 and emitter E2 of transistor Q2. Right? Now what will happen? See, when positive VCC supply has been provided, there will be a flow of current IC in this particular direction, right? Then there will be a flow of current IB, which is base current, in this particular direction. Okay, so collector current and base current are flowing, then emitter current will flow in this particular direction. Okay, and this collector current will flow to emitter resistance RE 2 times the IE, causing a drop across RE, right? And this base current RB will cause a drop across resistance RS. Okay, then there will be a voltage between the base and the emitter terminal, which is known as VBE. Okay, so this is my base emitter voltage VBE for both the transistors. Okay, so this is what we are available with. Okay, now these transistors Q1 and Q2 are identical in characteristics. Okay, and hence for such a matched pair we will assume certain parameters. Okay, what are the parameters? See, first, Q1 and Q2 have same characteristics. Second, value of RE1, RE2 are same. Okay, so what will happen to RE? RE will be RE1 parallel RE2. Okay, we have already seen this. Then if we talk about the collector resistances RC1 and RC2, they are same, and this is equal to RC. Okay, and also we have talked about the magnitude of supply voltage VCC is equal to VEE. Okay, and these both are measured with respect to ground. Okay, so whatever two transistors we are available with, they are matched and the circuit is symmetrical. So it is enough to find out the operating point ICQ and VCEQ for any of the two transistors. and the same will be applicable to the other transistors. Okay, so if we are succeeded in finding out the operating points for any one transistor, the other transistor is having same characteristics, so definitely the same parameters will be associated with the transistor 2, right? So now let us try to find out these two parameters, right? So we have this base emitter loop, you can see over here. Okay, I am talking about transistor Q1. Okay, so what we will do, we will apply KVL around this base emitter loop of transistor Q1, right? And let us see what we are getting. Okay, so applying, remember, whenever we have electrical network and if you want to find out voltages and current, we are going to apply Kirchhoff's law. To find out unknown current, we will apply KVL. To find out unknown voltage, we will apply KCL. Okay, so applying KVL to base emitter loop of transistor Q1, what we will get is, see, this base current is flowing through RS, okay, and it is going in upward direction like this. Okay, so negative IB RS will appear, right? So minus IB RS. Then this VBE, voltage between base and emitter, is appearing, minus VBE. Okay, then we come over here. Okay, there will be a voltage drop across resistance RE. It is 2 times IE RE. So minus 2 times IE RE, and there is negative voltage, minus VE minus VE will become plus VEE equal to 0. Okay, so this is what we are getting. But we know the transistor. Okay, we know some parameters. What are the parameters? The collector current IC is given by beta times IB, and this collector current IC is also approximately equal to emitter current IE. That is what we have seen in bipolar junction transistor in basic electronics of semester 2. So here you can see IB is equal to IE upon beta. Okay, so we are going to use these equations. Let us give the equation number. This is my equation number 1. This is my equation number 2. Okay, so we will put this equation value of IB in equation number 1 such that we will get minus IERS upon beta minus VBE minus 2 times IE RE plus VEE equal to 0. Let us call it equation number 3. Okay, so let us take IE common out of this, then it will be equal to minus RS by beta minus 2RE plus VEE minus VBE equal to 0. Okay, now let us try to find out the value of IE. So IE equal to VEE minus VBE divided by RS by beta plus 2RE. Okay, so this is the equation of IE. Now we know the value of this VBE voltage, the voltage between base and emitter. It is around 0.74 silicon and around 0.2 to 0.34 germanium, right? So we can write down VBE is equal to 0.6 to 0.7 for silicon, and it will be 0.2 for germanium. Okay, and we also know that this ratio RS upon beta will be very much less than these values. Okay, 2RE. Okay, so practically if we think, Rs by beta will be very much less than this parameter 2 by Re. So now the value of IE would be VEE minus VBE upon 2 times Re. Okay. So from this equation, we can observe that Re will determine the emitter current of the two transistors Q1 and Q2 for the known value of VEE. And the emitter current through transistor Q1 and Q2 is independent of the collector resistance RC. You can see there is no collector resistance RC in this equation of IE. Okay, so these two are the conclusions from our end. Now let us determine VC. Okay, IE we already got. Okay, and we know that IE is known and IE is approximately equal to collector current IC. Then we can determine the collector voltage of Q1, that is VC is equal to VCC minus IC RC. Okay. Okay. So here what we will do, we will neglect the drop across the RS. We can say that the voltage at the emitter of Q1 is approximately equal to VB, negative VB. Hence, the collector to emitter voltage, that is VCE, is equal to VC minus VE. Okay, VC is VCC minus ICRC and VE is approximately equal to minus VBE. Okay, so now we know the equation of VCE, which is equal to VCC plus VBE minus ICRC. Okay, so here IE equal to IC equal to ICQ, while VCE is equal to VCEQ for given values of VCC and VEE. Okay. So for both the transistors, we can determine the operating point values using these two equations. Okay, equation number 6 and this second equation is equation number 8. Okay. So with the same biasing arrangement, the DC analysis remains same for all the 4 configurations, possible configurations of differential amplifier, and hence we will get these two values. IE is equal to VEE minus VBE upon RS by beta plus 2RE, which is then reduced to this equation VEE minus VBE upon 2 times RE. Okay, so this is my ICQ value, and VCEQ is equal to VCC plus VBE minus ICQ RC. Okay. So these are the two equations which will give us the operating point. Okay. So DC analysis and expressions for ICQ and VCEQ remain the same for all the differential amplifier circuit configurations. Okay, if we talk about all the 4 configurations, then the value equation for ICQ and VCEQ will remain same. Okay, this is what we are getting with the help of DC analysis of differential amplifier. Okay, so we will try to solve some examples based on this DC analysis, and then we will move on to AC analysis. Okay, so what we will do with the help of AC analysis, we will try to calculate differential gain, common mode gain, and input resistances and output resistances of the differential amplifier circuit. Okay, so whenever we are finding out the other parameters, this analysis is known as AC analysis. Okay, so in the next lecture we will try to do AC analysis of differential amplifier circuit. Okay, so we shall stop here. If you have any questions, then you can ask.